Hello everyone! Welcome to another lecture for interactive computer graphics. You'll remember that last time we talked about OpenGL. That was an introduction to modern OpenGL. That was our topic. Well, today's topic is going to be introduction to GLSL, the OpenGL shading language. The stuff that we talked about last time around going to be very, very relevant today. We did a little bit of an introduction to GLSL. This is going to be a more proper introduction to GLSL. We talked about the GPU pipeline, right? So here's our GPU pipeline. We feed in vertices from here in the beginning from our CPU, and then it goes to our vertices go to the vertex shader. Vertex shader takes one vertex at a time, and then it outputs the canonical view volume position of a vertex. So each vertex shader execution outputs a single position. So if I have a triangle, I will have three outputs from three different vertex shaders, and it'll form a triangle when it arrives here at the primitive assembly and rasterization. Then the rasterization rasterizes that, generates the pixels, aka fragments, and those fragments one by one fed to this fragment shader, and the fragment shader determines the color of each fragment. And that goes to blending, and finally we get our final image, right? Last time around we talked about this entire pipeline. We talked about some basic fragment shaders and vertex shaders, and we mostly spend our time talking about the stuff that comes before that, right? Today's topic is mainly going to be about these shaders, this vertex shader and fragment shader. So I'm going to spend a bit more time discussing what they are and what they look like, and then we're going to talk about how you control them from your C++ code. So we're going to talk about the vertex shader over here and the fragment shader, right? So that's what we're going to talk about. Let's bring them up. And last time we saw very, very simple examples of these two shaders. So we had a vertex shader that looked like this and the fragment shader that looked like this. All right, so let's start with the vertex shader here. What's going on? In both of them, you'll see that they both start with the version statement. And that version statement is very, very important because different versions of GLSL had quite different syntax. So if you try to compile your GLSL code using the wrong version of GLSL, it's just not going to compile. So that's why it starts with this version number here, just to identify for which version of GLSL this was written. OpenGL tries to be backwards compatible and also forward compatible, but there were times in the past we had to break backwards compatibility. So this version stuff became important in time. So that's why we're starting with this. So this means OpenGL version 3.3 and the GLSL version that comes with it. So for the vertex shader up here, anything that comes above this main function, over here we're defining all sorts of inputs and outputs. In this case, our input is one input here, that's the vertex attribute. We only have one vertex attribute in this example. We call it POS, that's basically representing the position of the vertex. And we place that attribute to location 0 explicitly. If we didn't specify this, the compiler would pick a position for that attribute. So we had this input, we also have a uniform input. Now the difference between these two, which is very, very important, this one is a vertex attribute, that means it's different for each vertex. This one is a uniform variable, that means it's the same for all of our vertices. All right, for the entire draw call, this value is going to be identical for all of our vertices. So all executions of our vertex shader is going to be the same. So this is a very, very typical vertex shader actually. It's not doing much, as you can see. It's just taking this position, converting it to homogeneous coordinates by adding this additional coordinate here, and then multiplying it by with our 4x4 matrix that does the transformation. So whatever coordinate frame this position was, this matrix is transforming from that coordinate frame all the way to the canonical V volume. All right, that's its job. And this GL position is supposed to be a position in the canonical V volume, and the rasterizer is going to get this position, and it's going to rasterize whatever primitive we're rendering. It's going to be triangles mostly. So that position needs to be in canonical V volume. All right. So this is a very simple vertex shader, and honestly, this is going to be sufficient for your upcoming project. So just a vertex shader like this will be more than enough, provided that, of course, you set this transformation matrix properly, right? The vertex shader itself is not really doing that much. All right, so this is our vertex shader, and in our fragment shader, again, this is a very, very simple fragment shader, and again, this is going to be sufficient enough for your upcoming project, but we're going to talk about a bit more today in terms of GLSL. So again, it's starting with the version statement, and then it's specifying its output, and it's just outputting a constant color value. Now this is not very typical. So as I said, this is a relatively typical vertex shader, right? The primary job of a vertex shader is doing this, transforming the positions we feed into the vertex shader to the canonical view volume. That's its main job. I mean, you could do whatever you want inside the vertex shader. It's your code. You can do a lot of things in here if you want to, but this is its main purpose. Over here, the fragment shader is just outputting a single constant color, which is not very typical. Normally, we do a lot of computation here. To figure out what that color is supposed to be. And we're going to talk a lot about what to do in here in the context of what we call shading, that is figuring out what this color is supposed to be. We'll talk about that a lot starting next week. So don't worry about it for the time being. But for this fragment shader, we're just outputting a constant color. All right, so the funny thing is, in this format, our fragment shader is not getting any input. It's just has an output, which is kind of odd, right? If you look at the vertex shader, it is getting an input, and it is setting an output, right? But fragment shader is just sending an output. How do I get an input in here? I mean, I know I can get inputs here as vertex attributes, but how can I get any input into my fragment shader? I can get inputs to my fragment shader by specifying inputs, like so. So this is saying, hey, I have an input here. I called it vColor. It's a vector 3. It's a 3D vector. That's an input. Okay, what am I going to do with that? Well, let's say that I'm going to use that to specify my output color. Let's say instead of sending a constant color here, I'm just going to use whatever input I get here as my RGB component of the color, and 1 is the alpha value. Okay, good enough, right? Why not? The question is, who's giving me this value? Like, okay, I said that it's an input, but where is this coming from? It needs to come from somewhere. Well, it's going to come from my vertex shader, right? So if I have an input like this inside my fragment shader, I must have a matching output in my vertex shader, right? So I'm going to define another output inside my vertex shader here. So I'm saying my vertex shader is outputting this value, whatever that is. We call it vColor. So notice that vColor here is the same name vColor here. So there are two separate files. Yeah, but this name has to match this name exactly. And this is how the compiler, well, the linker more specifically, will know how to connect this output to this input. Okay? That's very important. All right, so I'm just going to output this. But guess what? This particular very simple vertex shader is not really outputting anything else than this GL position. Right? We kind of need to output that, otherwise it's not going to be valid. So if I have an output like this, I need to specify it. I can do that here inside my vertex shader, and I'm done. So as you can see, there's really no particular order in when you define the GL position versus this vColor. You can define them in any order that you want, as long as you assign something to them inside this shader. You're okay, right? So this is it's an example of how you send a particular data to your fragment shader. But again, this is not very interesting because, hey, I was outputting a constant color here. Now I'm outputting whatever I get in here, but what I'm getting is a constant color. So again, this is just outputting some constant color. Not very exciting, right? I haven't really accomplished anything by moving all this stuff to my vertex shader. Okay, so what can I do? I need to get something to specify this value. Now, I could just use my position to determine what this color is supposed to be. I could do all sorts of funny computations here if I want to. Or maybe I want to get a color value for a vertex. Right? I can do that if I want to. All right, let's say that I'm going to define another attribute. Instead of having just this position attribute, I'm going to have another attribute here. I called it CLR, short for color. Okay, that's another vec3, and I'm going to use that to specify this value, which is supposed to be vec3. So, all right, it all matches. I can do that. Instead of setting a constant color, I'm going to replace it with this. So each vertex shader execution will get a different position and different color value, and it will output a position and it will output a different color value. So by doing that, I can get different color values to my fragment shader, and then my fragment shader will just output that color value because I decided to write a very simple fragment shader here. Of course, these are going to be different colors, provided that I'm sending different color values to my vertex shader as vertex attributes. Okay, so last time we talked about how to set these attributes. So we know how to, we can have a vertex buffer object for the color and then assign it to the attribute at location 1, so that when we say GL draw arrays, it will be sent to our vertex shader. So, is this the only way of sending data to my fragment shader? Absolutely not. So I can send data. If I'm going to send buffer data, those buffers are vertex buffer objects, right? So if I'm going to send vertex attributes to my fragment shader, it has to go through the vertex shader. That's the only way. I can just say, oh, these are my fragment attributes. That means nothing like that exists, right? Because we're going to take the vertices, they're going to pass through the vertex shader, they're going to be rasterized. That's when I'm going to have pixels or fragments. And before that, I have no fragments. So I can't just send and say, here, this is my fragment buffer object. It's no such thing exists, okay? So I have to send it through my vertex shader. But I can send, just like I'm sending a uniform value here, I can send a uniform value to my fragment shader too. So just like here, I can have a uniform float intensity. Could be float, could be vec3, could be a matrix. So a whole bunch of types are allowed here. I can actually define structures and structs and set the values of those structs. Set each element of those structs. That also works. So in this case, in this simple case, I just assigned one floating point value as my uniform parameter that applies to all of my fragment shader executions. So why am I sending this to my fragment shader? Well, if you look at this, there's absolutely no reason. Actually, if you write a fragment shader like this and you compile it, the compiler will just get rid of this uniform value. Because we're not using it, we're not doing anything with it, so it'll disappear. It'll disappear when you compile. So you kind of need to use it for it to be useful, right? So let's use it. Let's say that I'm going to multiply the color with this intensity. Why not? All right, so with this intensity control, I can make my color darker if I want to. So if I set it 1, it's going to be the same color. If it's anything that's smaller than 1, it's going to get darker and darker. Good. So this is a very typical GLSL workflow. The code here, as you can see, it looks very much like C++. It's that C-like structure, and you can do a lot of things you can do inside C, as I said a little bit ago, you can define structs. Structs could be input, they could be output. You could even get vertex attributes as structs if you want to. So you can define your custom data structures and get your data like that if you want to. You can definitely have functions in here. I can define as many functions that I want, like C-style functions, and call them. In here you can have, obviously, you can have loops and all sorts of interesting things, very much like C here. And it has some additional flexibilities of C++, but it's mostly like C than C++. And also you could have macros in here. If-def statements, definitely you can have those as well. And they're very, very useful. If you define struct or functions in the vertex shader, do you have to redefine them in the fragment shader to use them? Yes. Absolutely, you'll need to redefine. In C, C++, we have this very nice, wonderful, magical statement, include. Right? Include statements. They're wonderful. We cannot have them here. Because this is going to be some texts that you send to your compiler at runtime. At runtime from your C code. So it's just going to be a string, and you send it to your compiler. Your compiler is getting that string and compiling it. So it has no access to your hard drive and to your include directories, whatever they are. So there is no include statement here. That's very, very important. When you start to think about defining the same thing up here and down here, wouldn't it be nice if I defined a header and then I included a header in both of them, and inside that header I defined my struct that I'm using for both of them? That would be very nice. I cannot do that. I mean, there are ways to get around it. Don't get me wrong. You can have different strings and then you can combine them together and tell the compiler to compile them. And so if I want to include some other file, what I need to do is I need to open and read the contents of that file, and then I can just put the contents of that file into wherever it's supposed to go. Basically, you programmatically include the contents of that file in here so that your compiler will have access to the contents of that file. Another way of handling this is actually sending multiple strings to your compiler. Instead of sending a single string that contains your entire code, you can split your code into multiple strings, and you can send your compiler an array of strings, and your compiler will interpret it as one continuous string from in the order that you provided. So you don't necessarily have to concatenate and get a larger string. You can just send all pieces one by one. Well, not one by one, but all together, and your compiler will be able to handle it. So include statements would be very useful. We cannot have them, but there are ways to do things that are similar. So this was the not so nice thing. There are some nice things about GLSL as well. One thing that I particularly like, and I want to show you this because it's not obvious, it's sort of going outside of the C syntax a little bit. So I can access the members of my color value here, like RGB values. I can also put RGB, and that becomes a 3D vector. Now in this case, I define my color as a 4D input, but I'm only using the first 3 components of it. So I'm getting 4D attribute. I'm just using the 3D components, RGB component of that attribute. And it has R, it has G, it has B, it has RGB, or you can actually change it. You can have RBG. That's my favorite. You can have RBG here as well. I mean, you can have whatever order you want, really. This allows you to swizzle the data, whatever data you're sending, and you can do the same trick inside the shader as well. Just move the red here, blue there, and it doesn't have to be red or blue. You can do XYZ coordinates with XYZ coordinates as well. In fact, look at this. This 3D vector, this is a 4D vector. I didn't say that this is a position. I didn't say that this is a color. right? So compiler has no idea that this is the color value, but I can say RBG, right? So I can also say XYZ. That's also fine, because it's the same thing from GLSL's perspective. So you can do the same sort of swizzling using XYZ as well. Is it allowed to print the debug message in GLSL? Absolutely no. No, you cannot print anything inside GLSL. Yeah, debugging GLSL code is going to be a little bit of a hassle. The simple, oh, just print something over here so I know the value, kind of old style debugging options will not be available to you. But you could use this output image as your debug output. You're outputting something, right? And if you're written enough code that so that you're seeing your objects on the screen at least, you can output certain things in here. And I'm going to mention this again when you're implementing more complicated fragment shaders. I'm going to suggest that you output some stuff here, some intermediate values here, and see what they look like. You can output them as some color values, and you can have some color coding of different values so you can take a look at them and make sense of what data you're getting. So you could sort of use this as like a debug output. Okay, so this is the workflow. As I said, these could be a little more complicated. We could write much more complicated shaders here, but I presume you get the idea. And my point here was to just give you guys an introduction to this. I will leave the rest to you to figure out what sorts of other things you can access and what sorts of other interesting things you can do. But I would like you to have this complete mental picture of how this all comes together. So when we think about this as like a single vertex coming in here and going to the fragment shader, it makes perfect sense, right? So if I'm just drawing points, which is going to be our topic for the next project, we're going to be drawing points. So if I'm just drawing a single point, one point here goes to, one point is one vertex basically. That one vertex comes in here and I output this value, and that output comes in here and that's what I display. It just makes sense. But what if I'm outputting multiple, well, what if I'm drawing something that's not a point? What if I'm drawing a triangle? In which case, a triangle will have 3 vertices, right? So this vertex shader will execute 3 times, probably in parallel, for these 3 vertices. And in this example, I gave a color attribute to each one of the vertices. So I should red, green, blue, and they will appear as this color value here. All right? So I'm sending this red, green, blue values as output V color here. And then I'm going to get these fragments, these pixels. Well, what are they getting? Like, which color value are they getting? Because they're not directly associated with any of the vertices, right? They're associated with the triangle. These fragments here, they're not associated with the vertices directly. So what's going to happen is that our rasterizer, when it generates these fragments, it will also generate the interpolated values for these fragments. To be more specific, it's going to generate the interpolated values at the centers of these fragments. So at the center points of these fragments, I will get the value. So these fragments are, we talked about this, pixels are not little squares. So let's think about them as like little dots at the center of each, that correspond to the center point of each pixel. So over here, if I'm outputting a color value here, my fragment shader will get the interpolated color value at whatever point it's computing. So this fragment shader will run multiple times, of course, one for each one of these fragments, and each fragment will get a slightly different V color value in this case. All right, so let's put these triangles away. Now, I'm going to do something else here. Let's say that instead of this intensity, my uniform value is, let's say I call it alpha, and I'm outputting that alpha value here. So what did I do? I am outputting this V color that I'm getting from the vertex, the interpolated V color value, and it's this alpha, this constant alpha value. Well, I'm calling it constant because it's a uniform value. It's going to be the same for all of the fragments in this particular draw call. So what's going to happen? I've got transparency. See, I'm changing the alpha value. Now I have transparent, semi-transparent triangles. Super easy, isn't it? Is it? Maybe? Well, remember we talked about this. Remember we talked about rendering algorithms? We said Z-buffer rasterization was nice and all, but it could not handle transparency that well. So yes, we can output an alpha value here, but that does not mean much on its own. It's just a value, just like red value, it's an alpha value. That's all it means. It doesn't mean anything else. It doesn't mean transparency on its own, right? But you can make it mean something. You can actually use this. So what's going to happen is that my fragment shader is just going to output this alpha value, and it's going to be written to my back buffer. Remember the back buffer, the front buffer, the swapping? Yeah, it's going to be written to the back buffer as the alpha value that corresponds to that pixel. Okay, I mean, I don't even see it because I see RGB, yeah, red, green, blue. Yeah, I see that on my screen. Alpha value, I don't even see. So yeah, it's just going to be the alpha value that's going to be stored for the pixel. Nobody will see it, so it's kind of pointless unless you do something with it. Now, remember, going to our GPU pipeline, I'm not outputting the value here directly to the back buffer. The output of the fragment shader goes to this blending stage. Now, in this blending stage, I can do things with that alpha value. This is like a fixed function unit, but I can change its parameters. I can make it execute sort of different types of blending functions. OpenGL will allow you to set what that function is supposed to be. Of course, there are limits. You're not writing your custom code to do this. This is a fixed function unit after all. So it's not going to be custom code, but it has a range of possibilities in terms of what kind of blending operation it's supposed to perform. And if you want to do alpha blending, which is probably what you want to do. So if you're not familiar with alpha blending, please look it up. I talk about it in the Introduction to Computer Graphics course. So you can perform alpha blending here easily. You just need to draw your triangles from back to front. So from further away to closer to camera. Triangle drawing order. And then you can set this function. You can turn on blending in OpenGL and then say, this is what you do for blending. And you can say, use the fragment alpha for doing blending because we're doing alpha blending. And then you can get an alpha blended image like this, right? So there's a way to use that alpha, but unless you do something with blending here, that alpha will just be recorded to your back buffer and then it will be displayed on your front buffer and you won't see it because it's alpha, right? It's not one of the color values. Now, this is what I want to talk about regarding the introduction to GLSL. So, we spent a bit more time on GLSL and that was our main topic for today. But there are other things that we kind of need to do to make all of this work. So let's talk about that. And all that stuff is going to be over here. Actually, it's not going to be over there. It's going to be on our CPU code. It's going to be a part of our CPU OpenGL code. Like what? For example, we'll need to compile these shaders. Now, we talked about this last time. You'll remember. We talked about how to generate a program. We talked about how to compile the shaders and then link them. There's a bunch of code here and there, but this is the main structure, right? So okay, I compiled my shaders, I linked it into a program. Now I have this program. When last time we talked about how to send attributes, how to take the vertex buffer objects that we're generating and attach them to particular attributes before our draw call, right? So we talked about how to set those vertex attributes, but what we didn't talk about was how to set the uniform values, uniform variables. So in my program, my shaders, in my vertex shader or fragment shader, I might have uniform variables, and I would like to be able to set those values, please. So here's how we do this. Before you set the value of a uniform variable, you'll need to get its location. That's a funny thing. Just like the, vertex attributes have their locations, uniform variables have their locations as well. We didn't explicitly specify a location, so we just need to ask the compiler, where did you put it? So remember, we had alpha in our fragment shader. Inside our program, we're not looking at the fragment shader, we're looking at the program, the whole compiled and linked thing. Inside our program, I'm looking at the position for this alpha, and I'm going to get the location here. All right, so it's just going to be an integer value that'll tell me what that location is. And then alpha is just some value, some floating point value. I can set its value like this. I call this GL uniform. This is the location, and then this is the value that I'm setting. Wait, I didn't say which program I'm using here. Oh, this function doesn't know which program's location is modifying. It's the same concept. So we're going to call GL use program, just like the concept of binding. Remember, we were saying we bind the vertex buffer object, so any vertex buffer related OpenGL calls that we have afterwards will be associated with that particular vertex buffer object. Same thing here. So I bind a program, in this case I say GL use program, and then all of the program related stuff is going to be using that very program. Okay, so as you can see, this function has a little bit of a funny syntax here. Okay, GL uniform, I get that part, and then there's this one, there's F. And that's a very, very typical thing for OpenGL, actually. So this one means that I have a 1D variable that's just a single scalar, basically, and F means float. So you'll see that a lot of OpenGL functions will have this type of syntax. So there's going to be the name of the function. It will always start with GL. It's going to be GL uniform, and 3 here means it's 3 dimensions, and F is float, so it's going to have this XYZ as its input. Now remember, OpenGL is a C library. It's not a C++ library. It's a C library. And C does not allow having multiple functions with the same name. Right? So I cannot have a single GL uniform function and I can call it with a whole bunch of different input. You cannot do that. In C, 2 functions cannot have the same name. So if you're going to have 2 different formats here, you're going to have 2 different function names. So this is how the function names are defined in OpenGL. So it's very typical. You will see many, many functions of this sort. Sometimes we want to, instead of sending these XYZ values, sometimes we like to send like an array, an array that contains the XYZ values. In this case, the function name will have this added v at the end. And over here, that means that v means that this is a pointer. It's a pointer to an array of floating point values that correspond to these XYZ values. Right? So this is how we set the uniform values. Also, this is the naming convention that OpenGL uses for its functions. Right? Now, if you're looking at OpenGL, you will also see functions that have some strange names besides these dimension, type, and optional v here. By the way, if this is f, that means it's float. If it's I, it means integer. If it's u, it means unsigned integer. B means byte, I believe. So all these functions have different versions of those. But there are other types of suffixes beyond these, 3fv here. These suffixes may look like this. For example, this glgen program also has this glgen program ARB. What is that? Well, ARB is short for Architecture Review Board. There's this other function, GL uniform 1, I64VNV. That means an integer of a 64-bit integer, and it's taking an array of 64-bit integer of just one value. So basically it's taking a pointer. And V is short for NVIDIA. So this is NVIDIA's OpenGL extension. So this was an old OpenGL extension from ATI, GL draw buffers. Yeah, ATI extension. So the way that OpenGL versions and extensions work is that when a new graphics card is coming out and it has some new features that did not exist before, we kind of needed to modify the graphics API a little bit and add some additional functionalities to the graphics API that were not supported before. For example, I think this is a very good example. This is a 64-bit integer, right? So, prior graphics card did not allow you to send 64-bit integers. And at some point, NVIDIA came up with this graphics card that could deal with 64-bit integers as uniform variables. So, we needed to add this extension to OpenGL. We need to have a function like this. And NVIDIA decided to add this function to OpenGL so that their users could start using this function. Now, this is not a core function of OpenGL. This is an NVIDIA extension. That's why it has NV in it. So OpenGL headers may be shipped with this, but it's not an official part of OpenGL. Typically, these type of vendor extensions then go into this ARB type of extension. Go to the Architecture Review Board and approved by the Architecture Review Board, and then it becomes an ARB type of extension. So it becomes that means it's an extension that's approved by the Architecture Review Board. That typically means that it will probably be placed inside the core OpenGL functionality in the next version. So in the next version, they move it to something like this. They just chop off that ARB part and we get the full function. So if you see a function that looks like this, and also it has an ARB form and maybe an NV form and maybe an AMD form, whatever, which one should you use? Well, you should probably use this if your graphics card supports it. Probably it does. So you shouldn't worry about it too much, that this one should work. But in most cases, it won't matter which one you use because they will be exactly the same function. They'll be exactly the same, different names for the same function. So, and OpenGL extensions work a little funny actually. So when you include this gl.h, this is going to be OpenGL 1.1. Kind of old, very, very old. Doesn't have any shaders in it. We can't do much. Well, we can do a lot of things with OpenGL 1.1, but not the version of OpenGL that I would recommend that you use. For newer OpenGL versions, they're not defined in this gl.h. So what do? Well, I need to include GL extension header. And of course, I need to find the latest version of the GL extension headers to make sure that I have the right extensions defined. Now, the tricky thing is that, OpenGL functions for 1.1, they're defined, they're defined as functions and I can access them. These extension functions, other things, anything that's in higher OpenGL versions, I do not have functions for them. Yeah, there are no functions for them. So what do? How do I mean, those functions exist somewhere, but in the GL extension header, they're not defined. In this header, they're not defined as functions. So what are they defined as? Well, they're defined as types. So there's this function pointer type. This function pointer type with a funny name. That's a function pointer type with a particular signature. It's actually, you'll see that there's going to be a line very much like this inside the GL extension header. So this is a function pointer. It's a type def of a function pointer. So it's defining a function pointer type. All right. So what we need to do is we need to ask our driver to give us a pointer to that function, please. So if I want to use this function, GL gen vertex arrays, I probably need that. So if I want to have a function like this, then I'm going to define it myself. It's going to be a variable of this type, and I need to get the pointer to that function. And for different operating systems, I'm going to be using different things to get the pointer to that function. On Windows, for example, I can use WinGDI, and WinGDI has this WGL get proc address function, and you can send the name of that function as a string, and it returns you the pointer to that function if your GPU supports it. Now, you shouldn't worry about it today. Back in the day, we had all sorts of different compatibility issues. So some GPUs supported some functions, some GPUs did not support, and there are different ways of querying whether or not my GPU supports different types of OpenGL extensions. You don't need to worry about that part today too much. But this is still a hassle. This hassle still exists. I need to get the pointers to those functions, and I can define those functions as variables in my own code so I can call those functions, which is kind of annoying. There's really no other way to call it. It's annoying. It's an additional complexity that we have to deal with. So, wouldn't it be nice if we could get rid of that complexity? Sure, yeah, that would be nice. So let's do that. So people came up with different ways of simplifying these things for the programmers. So one that I'm going to recommend is this glue.h, the OpenGL Extension Wrangler. So what this header does is that it includes the extensions, and then it does all of that initialization for you. You won't have to worry about it at all. So you just call this one time in your code, just one line. So, okay, you include this somewhere in your code, and then you call this in the beginning of your code, and after you generate your OpenGL context, that is. And then this will initialize all of these OpenGL extension functions for you. And you can call those functions as if they already exist. But after you call that, they will exist. Well, technically, they're still function pointers per se. But you can call them just like normal functions, just like they're defined in this header file. It won't matter. You just include this and then call this. There was a question about GLAD, just a different way of doing exactly the same thing. A couple of people actually asked if they could use that, and I say, yeah, sure. You don't have to use this. This is what I'm recommending because this is what I've been using, but if you want to use something else, that's fine. But I'm going to say, yeah, do this. All right, don't mess with this. I've done this way too many times. It's really not worth it. Okay, so this is the most efficient way of getting exactly what you need. I'm going to need, let's say, 3 OpenGL extension functions. I set 3 function pointers. I call them. I'm done, right? If I do this, guess what? This is going to initialize all of them, like all of them, hundreds of them. Yeah, it's going to be expensive. So when I start my program, I'm going to maybe wait an additional 10 milliseconds. So it's really not worth it. Just use this, okay? Just use this and be done with it, and then you won't have to worry about that at all. Yeah, do this. And as I said, doing this is super easy, but I want you to understand that there is this additional complexity that exists, and this header is hiding it from you. And if you don't understand that the additional complexity exists, it may be a little difficult to make this work properly. That's why I'm telling you all this long story, but in short, just add this header, call this function once, and you're done, okay? And then you're safe to use any OpenGL extension functions. Now, talking about funny extension-related complexity, here's this additional complexity that we managed to get rid of after a while. GLSL did not exist in OpenGL 1.0 or 1.1 or 1. Whatever. It actually started with OpenGL 2.0. In OpenGL 2.0, we had GLSL version 1.1. Actually, didn't it show up before OpenGL 2.0? Now I'm not sure. Anyhow, OpenGL 2.0 had GLSL version 1.1. Yeah, OpenGL 2.1 had GLSL version 1.2. OpenGL 3.0 and GLSL version 1.3. I mean, this was looking really weird, right? And at some point, I think this was a very good decision to drop that unnecessary complexity and say, you know what? If you're dealing with OpenGL 3.3, how about we call the corresponding version of GLSL 3.3 as well? Wouldn't that be nice? So starting with 3.3, that was one of the changes. Actually, I'm highlighting 3.3 here because this is where a lot of things change in OpenGL. Up until 3.3, OpenGL was fully, like at 3.2, OpenGL was fully backwards compatible. And that created a lot of problems for vendors because there was some old functionality in the API that no one uses anymore. But it's there. It's a part of the OpenGL standard, so you have to support it. And OpenGL 3.3 had new functionality, and that new functionality somehow had to work with the old functionality that no one uses anymore. And that created so much problem. So they thought that, you know what, how about we stop backwards compatibility here? So starting at OpenGL 3.3, we dropped a part of backwards compatibility. So starting with OpenGL 3.3, some old OpenGL functions will not work. So if you have an OpenGL context that is 3.3 and above, some old OpenGL functions that may still exist in the API, they will not work. Actually, they may not work. They might still, but they are not a part of the OpenGL core anymore, so the vendors are not required to support them. All right, so you may be lucky, maybe on your graphics card it works, but it doesn't have to. All right, so this old stuff that nobody uses and that existed for historical reasons that still exists in the API will not be useful. All right, so we dropped all that, and there are some other backwards compatibility issues moving forward, I believe. I can't really think of much. But anyhow, so when you generate a context, you want to use 3.3 and above. So if you want to have a particular version of OpenGL in your OpenGL context, well, you can't do that with GLUT, but you can do it with FreeGLUT. So remember I told you when we talked about GLUT, I told you that FreeGLUT was almost exactly GLUT, but just minor additional stuff. This is what it was. This is the minor additional stuff. So FreeGLUT allows you to select what OpenGL version you want to use for generating your context, OpenGL context. So you said before you create your window, you say, hey, I want to use this context, 4.5, and then it hopefully gives you 4.5. But if your GPU does not support 4.5, it only supports 4.4, you're going to get 4.4. So it gives you the best one. If you ask for 3.3, you can get 4.5 maybe. It's maybe because, with full backwards compatibility, it's okay. You get a newer context, but it still does has the same functionality, so it's okay. So, you're not necessarily going to get exactly this, but at least you can tell what you want to get. So hopefully you're going to get something that's compatible with it. And you can check which version of OpenGL you got after you created that window. You can actually query the OpenGL version. Another thing you can do, and you should do, is that when you're writing code for debugging purposes, enable this debugging flag. And that's going to be very, very helpful. So this will allow OpenGL to generate interrupts whenever there's an error. So you can actually receive error messages and process those error messages. I'll tell you how to do that in just a little bit. So remember, this was our overview last time. Now I added one more thing here. That's this line. We need to start with creating an OpenGL context and window, basically, and then create a vertex array objects, at least one, and then we're going to have a bunch of vertex buffer objects, at least one, compile shaders, and then for each vertex array object we do the assignment, which vertex buffer object goes to which attribute. and then we're ready to render, and then we start rendering stuff. So this was our pipeline, and this is what you'll need to do for the upcoming project. Now, to help with the upcoming project, all right, so to help with this, I'm going to suggest that you can use, if you want to, this code base, my code base. This will help you with some of your OpenGL implementations. I use the stuff in here quite a lot in my implementations, and I would recommend it. So, for example, I have this cygl.h, and in here, after you create your window, you can just call this macro, cygl register debug callback. When you do this, if you have any OpenGL errors or warnings, it will print that warning or error on your console window. You're going to see the error message. So if there are error messages happening, it will print it. And if you put a debug point into that function that prints the stuff that's inside this header file, then you can actually stop the execution of your code and see where the error message originated on which line in your code. So what this does is that it's actually creating this object, this GL debug callback class, an object of that, and then it's going register and ignore notifications. There are notification callbacks as well. I find them unnecessary. Or it's equivalent to initializing it with true, or it's equivalent to doing this. It's actually the same thing as the macro itself. So you do that, that will help you debug. Another thing is that OpenGL is a C library. I like C++ more. So I kind of like having like C++ objects, like a program being a program object. And then I have this function defined again in the same header file. Build files, you give it file names. Make sure that these file names are in the same location as your executable or wherever you're running your executable from. And then it will be able to open those files and read their contents and compile them and link them. So you won't have to write all that code. And if there are any errors, it's going to print the error messages and all that. All that code is written for you. If you want to write your own versions, just go in and check out what this function is doing. It's in the header file. Everything is written in there. You can write your own versions as well if you don't like to use this. There's a bind function. This basically is calling GL use program. And then you can call GL draw arrays. Right? So I would recommend that you use it because it sort of simplifies the implementation quite a bit. All right. Another thing that this class allows you to do is this funny syntax that I really like. So you could actually access it as if it's an array, and instead of an array index, you can give it a string. This is the name of my uniform variable, and then set it to my matrix, and it just copies that to your uniform variable. I like the syntax. It's a lot cleaner than calling the individual OpenGL calls, and it will compile exactly to the same thing. Well, okay, it's not going to compile exactly to the same thing. Every time this is going to ask the program for the location of the variable with this string, so it has additional inefficiency. Instead, you could cache that, right? You could just call that once, and then you know the location, and every time you're overriding that variable, you could use that location. So yeah, it's just slightly more inefficient, but negligible. So I like this a lot, actually. It just simplifies the implementation quite a bit. And what is this? This is a matrix type. So there's a matrix header in that library, and you could use that if you want to. And here's some examples of using these matrices. So this is creating a rotation matrix with this rotation value, a rotation around the y-axis. And this is creating a perspective projection matrix with this view angle, and this is the aspect ratio, width divided by height. This is the near plane distance and far plane distance. This is a 4x4 matrix, and this is a 3x3 matrix, and you can multiply them. In this case, it's going to treat this as a 4x4 matrix where the bottom row is going to be 0, 0, 1. So you can get the multiply matrix. So I'm not giving you the full solution of how you do transformations, but this should give you enough hints as to how you could maybe handle transformations. Another thing that you might need is this try-mesh class that will allow you to load OBJ files. Now, we didn't talk about OBJ files. I'll I'll talk about them a bit more later when we're talking about triangular meshes. It's a very commonly used file format in graphics. It's not the most efficient file format, but it's a text-based file format, and that's what makes it popular. You can just type it. It's a model file. It can store all sorts of different types of models. Great for triangular meshes or polygonal meshes in general. So this particular function, this particular mesh is a triangular mesh class. It's able to load OBJ files and parse them. So you just call this load from file OBJ, and it'll read the contents of that file and parse it and put all the data from that file inside this object, right? And you can access the data inside that object in various ways. For example, the vertices are stored in an array, and you can access them calling this function v. Mesh.v, 0 is going to be the first vertex, and if you get its address, it's going to be just give you the pointer for the array of vertex positions. For this upcoming project, you can exactly do this. You can read the model file, which is going to be a teapot, right? And then you can initialize your buffer with something like this. You say this is the size of the buffer, nv is the number of vertices, and this is the area of all the vertices. So this basically takes all of the vertices. Well, this whole code reads the vertex positions from this given OBJ file, and then this part just copies all that stuff to our vertex buffer object. Which vertex buffer object? Hopefully you created one and you did bind it, and then it will just copy it to that array buffer. That's the vertex buffer object. Okay, so this is what I planned to talk about for today, and we're almost out of time. All right, I'm going to say just a few things about the upcoming project. Now, this is going to be the simplest project in that when you think about well, it's not going to be the simplest. The previous one was the simplest, but this is going to be just a little more. But this might be, at the same time, the hardest project. Oh yeah, this might, if you haven't done OpenGL-based rendering before using C++, this might be the hardest project. Because the problem there is that unless you have everything in place, you will likely see absolutely nothing on that window. That's the frustrating part. Like if you're making any errors, and those errors don't have to be things that generate OpenGL errors. They don't have to be things that generate compiler errors. Your program may need to be maybe just working and doing exactly what you're telling it to do, but you're not seeing anything on the screen, and you kind of need to figure out why. So because of all these things, it has the potential to be the hardest project. So take that very seriously. Start it right away if you haven't started already. Start it as soon as possible. Because if you have any problems, if you end up being unlucky, and if you have any problems, that project may take a long time. But unfortunately, that's the way it is. You kind of need to set up everything that we talked about this week, and you need to set up everything just right for this to work. And if you have any problems anywhere, it's just not going to work. And that's the frustrating part. Yeah, we're not going to be doing much. We're going to be writing the simplest shaders ever. And everything that we're going to be doing will be the simplest version of everything that we're supposed to do. But still, putting it all together, that's going to be the big task ahead of us. So start early. That's my advice. All right, great. Everyone's happy. I'm happy. We're just about out of time, so we can end it here. Thank you. Thank you all for joining, and good luck with the project. I'll see you next week.